This is an example of another pretty well-known type of max-min problem. Sometimes you'll be given some kind of description of a function. So in this particular case here, you can see they're telling me that I have a function bounded above by y equals 25 minus x squared. That's an upside-down parabola. When x is 0, vertex is going to pass through 25 on the y-axis. It's going to look something kind of like that. And what they're saying here is we're making a rectangle that has vertices that are points on this curve, okay? So we're picking points there and there, we're making a rectangle, and the rectangle is going to go down to the x-axis, okay? So it's going to look something kind of like that. So the idea here is you can slide these points. You can make a taller, thinner rectangle, or you can slide these points down and you can make a short, fat rectangle. But those points always have to be points that are actually on this curve, okay? And we're trying to figure out what dimensions would make the largest possible rectangle. You know, would it be a perfect square? If so, what would those side lengths be? How is this going to set up? Okay? So a great example of a max-min problem. Remember, when you're working with max-min problems, you're usually going to be writing two equations. You're going to be writing an equation for the thing that you're trying to maximize or minimize. Usually you're going to have some kind of constraint or requirement that you have to meet, and that's going to tie in as well, okay? Most of the time I would encourage you to make a sketch and try to work some variables in. So I don't know the coordinates of that point. I go over x units, I go up y units. I'm going to call that point x comma y, okay? And those are going to be the variables that I'm going to use here. So if we're trying to find the maximum area, I first write the equation of the thing that I'm trying to maximize, all right? I'm trying to maximize the area. Area in terms of my variables here, if I'm going over x and I'm going up y, be careful there. The base of that's actually going to have dimensions of 2x, right? Because you're going x out this way and x out that way. The height's y. So the area would actually be represented as the base times the height, 2x times y, okay? And, you know, on the surface, you just say, well, okay, I want to find the maximum value. I'm just going to go graph this equation, and whatever the highest point is, that'll be the maximum area. But you have to be careful, because right now there are three variables. Okay, so the idea is you want to get an area equation entirely in terms of an x variable or entirely in terms of a y variable. It doesn't matter. You just want to get it down to a single variable function, not a function that's got two different input variables. Okay, so sometimes you'll have a constraints equation, and you know, maybe you have the perimeter has to add up to a certain total, or you know, you have a certain cost that something has to be, or something like that. The constraints here are a little bit different. This equation is the constraints equation. They're saying any point you pick has to work in that equation. All right, so this is kind of nice because I don't really have to write a constraints equation in the typical sense. We just know that it's y equals 25 minus x squared, okay? And what you want to do is you want to replace either the x or the y in this equation using the constraints equation. And you get yourself down to one equation with one variable, one function with one input variable. And you should be able to use a little bit of calculus to solve. So I'm going to replace the y with the 25 minus x squared. And that's going to give me that my area function is 2x times 25 minus x squared, okay? So you did problems like this probably in Algebra 2 and in Pre-Cal. They were probably always parabolas, and you're probably just finding the vertex, okay? If you notice here, if you multiply this through, this is actually going to be a cubic. The area is equal to 50x minus 2x cubed, okay? So that's going to be some type of a cubic function. It'll probably be doing, well, if x is 0, the area would be 0. So it's probably going to be doing something kind of like this. And again, lots of values on the function won't make any sense, okay? Having negative x values probably won't make any sense. This function hits the axis over here at 5, again, negative 5. So it's not going to make sense to have x values that are any bigger than 5 either. So probably your graph's going to cut off over here at 5, and then you're going to have a bunch of stuff that has nothing to do with anything over here and over here. Probably your maximum value is going to occur at that point, okay? And this is where the calculus comes into play. Basically, you need to figure out where the relative maximum is for this function, okay? Remember that the relative maximum or relative minimum occurs when the derivative is 0 or undefined. So that's going to be the primary calculus in most of these problems, is setting your derivative equal to 0 or figuring out where it's undefined. All right, so in this particular case, a prime is going to be equal to 50 minus 6x. Okay, sorry, minus 6x squared. And we want to figure out where the derivative would be equal to 0. Okay, so this is actually an abnormally simple equation. There are going to be times when it's a complicated derivative, and you might have to use your calculator to, the zero function on your calculator to figure out where it's 0. This one's really nice. So you can move the 6x squared to the other side. You've got 50 is equal to 6x squared. You can divide both sides by 6. So 50 over 6 is equal to x squared. By the way, I noticed something. If you divide both of these by 2, you get 25 thirds. If you simplify the fraction. Is equal to x squared. Then you can take the square root. By the way, you can take the square root of 25 and get 5. So x is going to be equal to 5 over the square root of 3. Okay, that's what the value of x is going to be where the maximum area occurs. Now, you need to be careful. Most of the time, they're not going to just say, oh, write an equation and solve for a variable where the maximum occurs. You really are going to want to go back and substitute that in. This is asking us to find the maximum possible area. Sometimes it'll ask you for the maximum possible dimensions. I would keep this as 5 over radical 3 for now, but remember at the end of the problem we may round to 3 decimal places. So let's come back here and let's see what's going on here. All right, so 5 over radical 3 is our x. You need to find a y value. And notice here that y is equal to 25 minus x squared. Okay, so most of the time you're going to be able to substitute in one of your other equations and find your missing value. So 25 minus x squared. X squared is just 25 over 3. Okay, that'd be 75 over 3 minus 25 over 3. Okay, and that's going to be y is equal to 50 over 3. X is equal to 5 over radical 3. And now you can fill that in, you can find your dimensions. So the height would be 50 thirds. Okay, the base would actually be 2x. So the base would actually be double this, which would be 10 over radical 3. And then they want you to find the final area. And of course now we know what x is, we know what y is, and you can substitute those back in. And it might make sense at some point here to round and kind of see what that would end up being. So you're taking 2 times the x value, so yeah, the whole length there is going to be 10 radical 3, but this is incorporating the 2 in here, so we actually just substituted the x value of 5 over radical 3. And we're going to multiply by the y value of 50 over 3. And if we multiply all that together, let's see, that's going to be 250 times 2 is 500 over 3 radical 3. And if you put that in your calculator, make sure you put that 3 radical 3 in parentheses. Let's see what we end up getting here. Okay, that's going to be approximately 96.225 square units for the area of the rectangle. Okay, or if they ask you for the dimensions, it would be a 10 radical 3 by 50 over radical 3. You could rationalize that denominator if you wanted to. That's the basic idea. So for most of these max-min problems, write the equation of the thing you're trying to maximize or minimize. Find a constraints equation using the same variables. Okay, use substitution to replace one of your variables. Get it down to a function in terms of one variable. And wherever your derivative is equal to 0, that's probably going to be a relative minimum or maximum. Now, I do need to make one other point here. When we talk about absolute maximum and absolute minimum, we'll talk about the idea that you also need to check the endpoints of the interval. Okay? Let me just briefly talk about the endpoints of this interval. A lot of these application problems, the endpoints of the interval just aren't going to make much sense. When I'm talking about endpoints of the interval, what am I talking about here? What's the smallest value x could be? X could be as small as 0, right? X could be as small as 0. X could be as large as 5, okay? If x is equal to 0, that means this thing has no width, and it has a height of 25, okay? A rectangle that has a width of 0 and a height of 25, it's going to have an area of 0, okay? So that's definitely not our maximum value. If x was equal to 5, this thing would just barely fit under that curve. There would not be any width left you couldn't have any height. So it would have a width of 10, and it would have a height of 0. And a 10 by 0 would also have an area of 0. So in this particular case, the endpoints don't make a lot of sense. But be on the lookout. You may see other cases where maybe there are endpoints for your input variable that you need to check where your maximum and minimum could possibly occur. So something to continue to think about. And if you haven't seen that other video yet, that may make more sense after you watch the video about relative max and relative min compared to absolute max and absolute min.